Thank you very much. Out of people here, so I'm gonna present about this interesting topic, but I'm gonna tell you the whole story, so you get the context and you get the challenge and the opportunities you have with this topic. So I'm gonna talk about data science applied to industrial applications. I'm gonna say why dynamics are important and why you need to be careful when you are doing machine learning in these situations. I'm going to say as well why, what is optimization, how you are using optimization every day, what is dynamic optimization, which is another layer of complexity, and some examples with a library written in Python that solves this kind of issues. So this is a very brief summary of what we chemical and process engineers do, applied to beer and whiskey. So we mainly do two things. We transform and we purify. We transform basic ingredients into something we can sell, which in this case is beer, and we can purify the beer so we can produce whiskey. The way we do that is there are two extremes on how we do that. There's a batch, and there's continuous. A batch is what everyone does when cooks. You do a batch, you cook a cake, you need more cake, you need to cook again. Continuous is another way, completely different. It's continuous feed of ingredients and continuous feed of products. And this is very important for the talk, okay? Because continuous is usually performed in steady state, and that has a lot of implications, especially when we want to do a batch. So you have a very common picture of the alambics that produce whiskey, or these huge towers, which is a continuous production of purification, continuous purification, okay? And the same for reactors. When we talk about reactors is usually kind of a deposit where we produce this chemistry. So industrial data science is data science applied to industrial topics, which should be around in the middle of this Venn diagram. So we have to combine obviously IT, computer science, math, statistics, and very important domain expertise. Not only data science, but please more of this. Why I'm saying that is because unless many other business, they have the challenge of digitization to get data. But oil and chemical companies or manufacturing companies, we usually have a very good data set because it's our business, we produce, and we want to have a record of what we're doing. So always we have a layer of control and actuators. This is a computer that is already in the plants, trying to make sure that all the plants run accordingly. We have a database we call data historians, or MES. And this is where we store years and years of data. We have a lot of data. And then on top of that, we start doing industrial data analytics, which sometimes combine planning and scheduling applications. So I'm going to give you an example of just a process that, suppose we want to optimize this cooling or substrate that is moving at a certain speed, and we have a jet, so we want to maximize the efficiency of the process, and we have two extremes to optimize this. We can go completely to first principle, we can do CFD, we can do amazing computations here, or we can go now with all the people like, no, this is data science, this is machine learning, because it happens that I have 2 years of data of this. So I will put my neural network, and I put my data science people, and I will solve it. So the question for you is, which do you think is better? Who thinks this machine learning is better? No one? Who thinks that first principle is always better? Okay, so you are a good audience. It's the middle always, never extremes, always balance. So what I'm going to say now is something I usually say, that in my opinion we have been doing in engineering, not only chemical engineering, but every type of engineering, kind of machine learning. But we didn't call it machine learning. For example, in this one, when I was studying this kind of equations, I was always bothered by why this coefficient is 0.48. And the reason is the data is a fit. We're fitting data into equations. But what you can see here, these numbers are kind of what we usually call in machine learning feature engineering, dimensional interreduction. All of these things are actually what we were doing to fit data into our process. So it's another name with less data, but it's the same idea. Similarly, we have flow maps, which is very common in your studies. So for example, here we have two fluids in one pipe, and depending on the velocity of this fluid, we will have different regimes of flow. And obviously, at low velocity, we have a very low sheet of water, and at high velocity, we have this kind of annular. So this can be seen either as a clustering or as a classification model, depending on what you're trying to do. Maybe you don't know you have many different regimes, and you have a lot of data, and you start to cluster this together, and you find these groups. Or maybe you already know these groups, and you want to understand with a new input where we lie. Anyway, it's kind of machine learning. And the oldest reference I found was 1973 of this idea. So you know that the old machine learning is about input. Instead of having to give them the logic, because I have a bunch of outputs, I will reverse this and will get the logic from the machine learning. And there are these three kind of extremes where I know the output, so it's a supervised, where I want to find the kind of aggregation or clustering. And the last thing, which I'm going to talk about, is how I optimize. You call this reinforcement learning. We call it process control. A very similar reinforcement learning methodology is called model predictive control, which is the talk I'm gonna do. But before that, everyone knows neural network. How many have used or know decision tree before? And how many neural networks knew or used before? Because in my experience, everyone goes directly to the one on the top. But the decision tree is a very simple algorithm to see nonlinear effects and have an explanation of why it happens. If this pressure is this one, and this pressure and this temperature was that one, but this valve was open, you will be in troubles. And when you combine a bunch of these, you have famous random forest and similar algorithms, which also resemble to something we call fuzzy logic. So we always want to keep an eye on what is the past of process engineering and process control and try to improve with machine learning. But we don't want to reinvent the wheel, which is very easy if you don't know what was the technology before. So common example, I have always time series because my data happens over time. So there is a lot of time series analysis, but it's not, we have a process and it's a different idea. So the commonest step is, let's say I have three variables over time. We have pressure, temperature, and flow rate. So you're gonna try to optimize the pressure, try to get the most of the pressure or the minimum of the pressure, and I'm gonna make something very simple. I'm gonna just say, things should move together, pressure and flow and temperature. So I'm gonna just put the correlation between temperature and flow, and put in the third dimension the color of the pressure. And I will forget about time. This can work in certain situations. If it's steady state and the dynamics are under control, it might work because I will have several use cases, let's say here will be or either a pattern or several clusters here that it will give me an idea on how to optimize. But you are probably gonna fall in a very, very common mistake because we know all of that trick of machine learning is about splitting your data, training and validation. But when you're in a time series and you forget there is a dynamic process behind, you're prone to overfit without even knowing. What I mean is, imagine that this process, which I have here certain variability, I have a huge sampling rate. I have data every second. And I'm measuring the pressure and the temperature of a huge tank. And the tank will take a while to cool down or to be heated. So when I do a random split of my data here, training and validation are going to be very, very similar. So if I just use this methodology to validate my modeling, forgetting about the time, forgetting the dynamics, I guarantee you're going to be in troubles and probably you're going to be overfitting. So you know that about the time series modeling, it's always better to use this kind of approach where you have sequential splits. And in any case, always, whatever you do with training and validation is not important as is the test of your time or your data. Because remember, validation doesn't mean the model is valid. It means that the model, in theory, shouldn't be overfit. It's a bad name, from my opinion. Another common mistake is that I forget about the process is not only steady state, but also in under control. So I have, for example, a tank, and I want to control the temperature of this tank with a refrigerator jacket. And then I start to look at the data, the distributions over time. I don't think about anything else but the variability of my data. So this is an example where I have certain variability, but if the scales are not right, I might think that this is super stable. And for a data scientist, something that doesn't move doesn't matter, because I always find correlations of things that move together. So a data scientist can come in and say, look, I found that this is super important. Temperature, forget about it. It's always fixed. But it's completely the opposite. Because I know the temperature is important, this shouldn't move. And I use the flow rate to make sure that this is under control. So if you don't talk with the process engineer or the control engineer, you might be trying to optimize something that's actually what is the target is completely the opposite. You will try to optimize perturbations, you will try to optimize things that you will try to fight against the control of your plant. Okay, so with this introduction to the problem, we have enough to talk about machine learning for dynamic systems. And always you have to think about and ask the right questions. What is the nature of your data and what is your goal? We love to get me the data and I will put it into machine learning and I will not think about the goal. Maybe the goal is not well defined. Maybe the goal is mistaken. Maybe the goal is just save money. That's not the goal, that is the business value. So what is the nature of our data? Our data is important for us, the dynamics, probably this, depending on your goal. You need to think about the quality and quantity. In chemical processes, sensors are usually bad. So we need to, or not bad, but there are many things happening. There are many operations, many shutdowns, many different things within 2 years that if you don't know, it might seem like bad quality data, but you have to be always thinking about the nature of that data because it might carry more information than you think. Observability, another issue. We cannot measure everything. We measure near the surface of the pipe. We cannot measure the temperature inside because maybe the sensor will be damaged. So it's always good to think about what is the observability of your model. And the most important point for today is the extrapolation versus interpolation. So who thinks that what we do in machine learning is extrapolation? No one. I think everyone knows that we usually use machine learning for interpolation, right? What if I tell you that you can use machine learning for extrapolation? You will call me crazy. And I call them crazy as well. But there is something called model discovery, finding of governing equations. And this blew my mind when I saw it. Because basically, if you think about the dynamics and you use machine learning for the dynamics, you can learn dynamics. You can learn differential equations with machine learning. And if you want to take one thing with this talk, is with this kind of work. So I don't care about the pressure or the temperature over time. I care on how the pressure, and how the temperature, or how my target change over time. Because if I only care about how change over the distribution over the years, probably I will find factors that are seasonal. Probably I'll find things I cannot control. So what can I do for the next instant in time, improve or control my process? What can I do to change something over time? And this is very, very important. Because if you put your target over the time and you don't care about how the target changes, probably you will not find things that you can change in that period of time. So always think about your target changing over time. If you think about it, if you have a lot of seasonality and things that you don't care, when you have a difference between 2 consecutive times, the seasonality moves away. It's a very common no. But you can go further. You can go to the dynamics. You have a system that changes over time with some certain inputs and parameters, and you have as well things that you can measure, because remember, things that change maybe are not measurable directly, so we need always to think about that. An example. Let's generate some data from the Lorentz system of equations, and we are gonna use the data to try to see if we can come back with this set of equations. We put ourselves in a situation that I only have the data of 3 coordinates, x, y, and z. What can I do to learn the differential equation, and hence, what can I do to extrapolate the model? So what I can do is think about the nature of my data. Think about a dynamical system is what I'm looking for. What that means is that we know that if you have ever studied partial differential equations or any kind of system, there is certain patterns, certain math that is always in every different problem. How the energy changes is the same equation as how the concentration diffuses or moves. It's the same. We're changing the temperature by the concentration, but it's the same. How a fluid moves is also a very similar equation. So if we go and we see each parameter in each of these differential equations, and we put all of them, I don't know which one is important, I will put all of them. And then I try to find, with this model, I try to find the parameters that are relevant to my problem. What are the coefficients? I'm putting all of them. But I can use lasso, I can use any kind of penalization for that. And if I am lucky and that my data is right enough, I can come back with the differential equation. So I'm gonna repeat the steps. You get your data, x, y, and z. You get the difference of this data, and then you put all of the parameters, all of the different combinations of your variables or your terms. There are libraries for this. And then you look and you try to reduce the number of the problem, and then you get back the terms. So for example, this was the original equation, and I have 3 differential equations, 1, 2, and 3, and I see that I got 2 coefficients for the one in x and y. So if I multiply this back, I see there is a positive and negative. If I do the same for the second, I see there is a combinatory term here, a nonlinear term, and I see that here. If you extend this one, you will find it, x and z together, and so on for these 3. I'm just touching the surface of this area of research. I have here a link. It's a professor in Washington, and he has. I mean, this seems intimidating, and it is, but if you go to the website, you will find himself teaching you about this in a nice video tutorials. It is great to get ideas. Okay, this is Professor Kutz from Washington State University. And by the way, I found this content in a summer school in Leiden University, in the Lorentz Center, so keep an eye on the Lorentz Center in Leiden because they have amazing workshops in summer, okay? Okay, well, let's go further. I have a model. At the end, what I always want when I have a model, coming from data, coming from first principle, coming from these 2, I want to optimize something, I want to change something, okay? So I have always certain inputs and my output, which I want to optimize. I can allocate things differently to maximize profit or reduce cost. I can design different systems to make them more robust or lower cost. I can control things better with optimization. And the targets are always maximizing your profit or minimizing your cost. But what the target is always clear. What makes these problems tricky are the constraints. What are my limits of the system that I cannot surpass because it's not safe, it's not possible, or any other thing. So that constraints is really the tricky part of optimization, because you have to make sure that, if possible, you have to define the problem in this way, in a convex way. So that will be, if I'm lower than here, it's not safe. If I'm here, it's not efficient, here things will break. And it's the way you define the problem what will help you or will completely jeopardize your solution. For example, if you don't care about this and you just put the constraints as they are, probably you're going to have a non-convex region which will make you difficult to find the optimum, the global optimum. And after these nice graphs, it's time to see a little bit of how you define this mathematically. We have seen this in many other talks. And this is how you define mathematically an optimization problem. You always have a function you want to minimize. If usually, as the professor said yesterday, we always talk about the minimization, but it can be maximization. It's just a negative of that. Then we have a series of constraints, as I said, the most important part. And then depending on what kind of equations we're putting them to solve, the problem behaves either linear or non-linear. So you can imagine that a nonlinear system is very difficult because the more linear is, as in any other model, is easy to understand. But unfortunately, very difficultly, the problems will be non-linear. Maybe they're non-linear in one region, but probably we will have a limit soon. So you see, this is kind of the language you have to get used to. You have your constraints. Constraints can be equal to something if you know exactly that what gets in has to get out, or it can be kind of no more than this, or in a range. There is another more thing on optimization, which is what if my variables are not continuous, or what if they are discrete? What if I'm trying to, when talking, for example, the elevator has certain levels, only 1, 2, and 3, and 4. You cannot be in the position 1.2. Maybe they are in binary. Maybe this is in operation or this is in washing. You cannot be in one or the other. So these are the what is called the integer variables. You know integer very well. And the way you can visualize that is constraints are here. All of that is not possible. Here we have in the background the maximization or minimization function. So we have kind of a projection of that function in here. And some variables are discrete, so I can only be certain operations. So does it look like this is for you or not? Because maybe not defining mathematical problems, but every time you produce a machine learning model, you are optimizing the error between your model and the data. So you might find this like far away from your interest, but you have to be aware that every time you solve any machine learning, it's an optimization problem. So with all of that language, you can understand what is commonly in the areas of optimization. It's an LP, it's an MNLP, it's all of that. So what it's like is, if it has integer variables and it's non-linear, it's an MINLP, and if it's very simple, it's a linear programming. QP is for quadratic. Now, there is a trick. We presented in 2016, I believe. And let's say you didn't have the exact equations. You cannot, or maybe the equations cannot be differentiable. So you can, if the problem is small, and the cost function, what you want to optimize is fast to obtain, you can use population or stochastic methods. This is a very less common than genetic algorithms, but it's also very interesting. It's called particle swarm optimization. There is a talk we gave in 2016 where we have like crazy functions like this one. And you know, every time we talk about optimization, we put a nice parabola where it's obvious where is the maximum or minimum, but the reality is usually that it's not clear where is the maximum or the minimum. Okay? And finally, dynamic optimization. We made it through here. So standard mathematical problems are defined this way. Minimization with certain constraint, equal or lower than equal. And we usually want to perform the automatic differentiation because we use the derivatives in these methods. And there are several languages. There are, and there is Ample, there is GAM, these are commercial. Payomo is an open source. Where is Sandia? Jump, which is, I think is from Julia. Casadi, which is a multi-language library. But we move from here to here. So now we move from the algebraic equation to a differential way. Because again, I care about how things move. So if optimization is complex, when we have something that we need to define dynamically, and this is very common because things are that complex that I can only tell you when this thing is going to be in the next time, in the next second. I cannot tell you when it's going to be in 1 hour because it depends on many things. So there is no other way to use how things move step by step, how things changes with the differential. So I'm going to talk about now Gecko, which is the optimization library, and what Gecko does is amazing because you only need to put the equations in the way you find in the books or in the literature, and then it will transform this to the algebraic equation for you. So it will move from this one to this one automatically. You only need to put the equations as you want. Gecko is a Python library, finally, something about Python in this talk. So we have Gecko can be installed directly with pip. Yeah, it's well documented. You have 18 examples you can play with. It's coming from a research group in BYU. This is Professor Hedegren, who kindly shared part of this presentation. And we have this algebraic modeling languages in Python that can be solved. All of these things I was talking about: linear programming, quadratic programming, nonlinear programming, mixed integral linear programming. No, you know the deal. So it's easy to install, easy to use. I'm going to show you some examples. So this is a common problem. You don't need Gecko for this. There are many other packages to solve this, but pay attention to the syntax. So I have my function I want to minimize. I have a series of constraints. These functions, these values are between 2 values. So that's exactly what I give. I go, this has to be between 1 and 5, and I have initial conditions on here. And then I have, which are described in this part of the formula. Then I just need to put the equations that are the constraints. So here we have these 3 or 5 terms need to be equal to 40, and this has to be equal or lower than. It's exactly as you find in the books how you can define this in the software. And then you say, I want to solve this steady state optimization. There are several modes, and then you have it. You have the optimum solution. Now, more interestingly, where you have a dynamical system, very simple differential equation, you only need to say that the differential equation is kind of an object of dt. And with that, you will be able to transform this continuous and differential equation into a discretization of the problem. Another example, this one is a little more complicated and most common to what we do. We have to optimize the integral of something. So I can add another variable and make a constraint saying that this variable has to be the derivative of the integral. And then I have this new formulation that I can directly put into Gecko. Here I can see that this is the first the differential equation and the second. And the rest is more or less the same you saw. And all of this brings us to the predictive automation because we have dynamical systems. We have dynamical systems. We have PID controllers, which basically look at the error you have done. And then it gives you the output. So it's a direct correlation between the current error, the past error, and the immediate future. But there is this model predictive control, which is, they have similarities to reinforcement learning, which you can do with Gecko, that what it'll do, it will look into the future with several steps. And it's way more powerful because you can look ahead. What series of action can I do to optimize this? And the model doesn't need to be perfect because every instant you will repeat this operation. So in this Gecko has also a product which is called this Arduino controller, and you have here an example of what I mean. You have your temperature measure, your set point, which changes suddenly. You're playing with this high up, and the heater, which is the actuator, which moves accordingly. This is a PID controller. So basically, you're waiting to see the error with the difference between these two to act. But with model predictive control, you can have kind of the prediction, which is the continuous line, and then the actual measurement, which is the discontinuous, the measurement, the discrete measure. And there is more in Gecko. You can even do a filter because it's very important that you have a filter of the current data to make a decision on the future. So what you can see in this band is a moving horizontal estimation of the current value to make your future better. You have many resources in Gecko. You have online course if you want to learn about this. It's not only about the library. There's also teaching materials. There are other tools, as I said. And the conclusions, I think, are that dynamic optimization is important to improve even further your processes, and that among all the challenges, machine learning can be used on top of what we know to get the most out of the processes. And that's all of my time. Thank you very much. I don't have any time for questions. Quick one? Okay. Thank you. That's an excellent question. Can you use feed-forward neural networks to model dynamical systems? I say no months ago, and I'm wrong. You can. And you can ask Professor here, Antonio Chanona, for that, and we can talk about that. Thank you very much.